Chapter 8, Troubles with Distributed System. We need to deeply understand what are some of the issues when we try to use distributed system, right? So in a distributed system, it typically uses commodity hardware and it's connected over the network. That's a typical distributed system. Whereas a monolithic system, there is no connection, there is no sharing, and there's no network involved. It's like one beefier machine which just gets bigger and bigger, and you have to buy custom software to run that machine. It has custom network topology and a lot of custom hardware that goes into scaling up a monolithic system. So there are many issues, especially when it comes to cost, that make it very difficult for us to scale up using a monolithic system, right? And so distributed systems way to go. But scaling is not the only advantage that a distributed system provides. We talked about in the previous videos, cost is something that is a big plus point for a distributed system. You can scale up using commodity hardware. You don't have to buy custom hardware. You don't have to buy custom operating system. You don't have to buy custom network configuration, topology, and a whole host of other things. You can scale up with commodity hardware, commodity network, right? So cost is a big one. Scaling is another big one. There's a limit at which one big machine can get enough power to serve millions of users, right? But here you could distribute it across multiple machines. So scaling and cost are two big advantages. But the third and the most important one is when we build distributed system, we are having a use case where we are serving global audience, global users. They require fast and effective turnaround time in terms of latency, right? So you want to keep your machines that serve the audience closer to the audience, right? So there's geolocated. So you cannot do that with one machine. Now it's one machine for the whole world versus thousands of machines very close to the user who's using the system. So typically, lots of advantages of distributed system, but there are three big things that we need to understand as to what are the three big issues. So in this video, we're going to go over that. The number one is clocks and reliability and unreliability with clocks, because now you have multiple machines have a different concept of clocks, and how do we deal with that? Second, process pauses, right? Here, nothing is shared, right? So one process can go down and then the other process needs that data from this process. So process pauses, right? That can happen and that can impact the overall machinery. And then the third is that there's this new thing called a network, which is connecting these machines, which doesn't exist in a monolith, right? So those are the three big areas that we will go into. So think about this. When you have a monolithic system, and let's say you have a software, you put an input A, it always gives you output B. It's deterministic, it's reliable. You can expect your software to give you the same output every single time with consistency. If you put in a username and the password and it's accurate, then it's always going to work. But if you put one digit that's not accurate, it is never going to work, right? So it is deterministic, right? So why is this important, right? This is important characteristic when you have an isolated system. But when you have a system that's not isolated, it's connected by unreliable things in between, like the network, right? It's unreliable. And now there is shared nothing architecture. So now there is dependency from one process to the other. Then deterministic property of the software is challenged in a pretty big way. It's very hard to provide the deterministic guarantees if you are using underlying systems that are not deterministic. So that's what causes all of these problems, right? So it's very much important to know that software is deterministic, but it's in isolation. But now you connect it with reality. When you have to scale it up and you have multiple machines over a commodity network, then it becomes undeterministic because of various dependencies it has, right? So knowing that, it's very much important to simulate failures. And so those real world practical failures, right, that you can anticipate, you need to simulate them before it happens. Like, let's say you reduce the network capacity artificially and see how the system responds. Does it get to a grinding halt with a deadlock? Does it never recover? What happens, right? So all of those situations need to be handled, especially when you try to scale up a distributed system. And so remember, if there is a problem that can occur, it will always occur. And so in this case, it's very much important to do that simulation and actually make your system much more harder, right? So we went over the two different differentiation for monolith versus distributed. right? So we'll go over them very briefly. So monolithic system typically end up using custom hardware, custom network topology, like to actually get those interactions set up, custom everything almost, right? You even the vendors will charge you heavy money for the setup, right? For scaling, and there's also limitations of power and capacity at which you will run out. Even upgrades, think about it. If you want to upgrade your software, this a lot of them may require you to pay a lot of money if you don't want to have downtime, right? So upgrades is very difficult, right? And but the benefit is that there is no huge network dependency between processes, between systems here. But in reality, when you start to use a distributed system, a lot of things can go wrong, right? This network could be a cable across the Atlantic, right? And then a shark could come and eat that cable, or there could be some human error, like in your data center, right? There could be an accident, a bad configuration. So a lot of those things can happen in a distributed system because it's not isolated. There are many more factors at play, many more people, many more systems that are connected. So distributed system is differing that way. But at the same time, it's opposite in many other angles. Right? It doesn't use custom hardware; it uses commodity hardware, so it's cheap, right? It doesn't need a custom network topology. It uses existing internet setup that we have and network topology. It has nothing shared. Here there is shared everything, right? The multiple processes can share the memory, and so they can use all of those locking functionality that the operating system provides. But here you cannot lock, this process can't lock on this one easily. You can, but there are many ways to doing that, right? So there's many differences between a monolith setup and a distributed system setup, right? Even here, when you think about this, there are multiple queuing that is going on, right? There's a queue for the network, right? There's a switch layer, there's switches in the network that can queue up your packets. There could be operating level switches. There could be their operating level queues. Virtual machines will have their own queues of how those packets are handled, how those processes are handled. So there's a lot more dependency that's going on here, right? So that's an important aspect to remember. There's a lot of queuing happening in the distributed system, right? Also, machines can go down, right? And so it's very much important to understand when a fault happens, when a machine becomes unresponsive because something happened. Maybe the power went out, maybe the configuration destroyed the process, or the process got overwhelmed, or maybe it's going through thrashing with page faults, right? So a lot of things can go on. So fault detection through timeouts is an important characteristic that the distributed system introduces. Also, a lot of the systems have multi-tenancy, meaning you share your compute resources with other websites or other, it's a shared infrastructure, right? So that's why this setup is typically called the cloud setup, versus this is the high performance compute setup, HPCs, which is the monoliths, right? So cloud versus HPC is another distinction you can have to distinguish between these two, right? But also think about this. This is deterministic, is optimized for deterministic throughput, deterministic outcome. But here, distributed system is optimized for opportunistic outcome. Meaning, if you can download, a gigabyte in 10 minutes, then it will try to do it as quickly as possible. The TCP layer will optimize for that, right? But here, it's not optimized for that, right? But opportunistic setup, like in the distributed system, has a lot of downside, right? It's set up to be opportunistic so that things can get done quickly. It doesn't, if the network is open, it can utilize as much as possible, but it can also cause congestion. So when congestion happens, right, there's no guarantees in which how quickly you can get that video call to be perfectly set up. Like, let's say you are on a video call with someone and you realize that there is slowness, their frames are not coming through, the voice is getting cut. That's what happens when there's congestion. So that's a downside of opportunistic setup. When everyone tries to use a lot of those internet shared infrastructure in the network, or even on the CPU, if there's a tenant next in your website, that the computer that's hosting your website, and let's say there's another website on the same machine, that tenant can have an impact on your performance, right? So that's the shared piece that can happen. And so distributed system is opportunistic throughout, from the network to the compute to the storage, everywhere, right? But opportunistic causes congestion. If you have a noisy neighbor, right, then it could have a lot of problem. So those are the two distinctions. So now let's go into the three big areas, right, we talked about. So number one, clocks, right? If you have one machine, you have one clock. If you have 100 machines in a distributed system, you have 100 clocks. So who makes sure that the clock is accurate across all machines? Like, let's say this machine says it's 9 a.m., but at the same time, this machine says it's 9:20 a.m., and this one says it's 9:10 a.m. So if a transaction happens here and here at the same time, it would feel as if this transaction happened earlier than this one, but it may not be the case. So clock synchronization and clock synchronization guarantee is very much important. So typically, how does the clock work, right, in the computer? So there's this quartz crystal oscillator that is used as a hardware inside every computer that gives you the notion of time and clock, right? It gives that constant, it moves at a specific rate, and so you know what the time is. And to synchronize these time, but these are hardwares that can switch, and they don't have reliability. They're highly reliable, but then they're all different. They're all different quartz crystal oscillators, right? And so those differences can exaggerate over time, and so those differences need to be synced at some point so that everyone's in the same time zone, right? You might have noticed when you buy a new computer and connect it to the internet, or you have a new cell phone, it automatically has the latest time. How does that work? It's a network time, right? So there's an NTP sync, which is a computer, and you can think about it, which tells you what the time is, right? And there are a series of such computers, a network time protocol that can give you what is the time, and then you can synchronize with that. But again, there's issues there because it depends on the network round trip, on how quickly you can get that time. And if it takes more than 10 milliseconds or 20 milliseconds to just get that time, then you may be out of sync already, right? So remember that it uses hardware that is not deterministic across machines, and everyone would have some drifts that you have to take care of, right? So that's why and also in our system, there are two types of clocks, right? One is a monotonically increasing clock, and one is a time of day clock. In Java, you can get system.nanotime and give you the monotonic clock, and system.getCurrentTime give you time of day clock. Remember, when you want to time how long something is taking, you don't want to use time of day clock. You want to use the monotonic clock so that you can actually time how long it took, and it's continuously increasing, at least from the relative space of that current machine. So clock sync, clock drifting, and syncing is very much important when you have to deal with validity of a time in a distributed system, right? But if you don't do it, right, then there'll be silent data failures, right? Data loss could happen because if you have the last write or win logic, then you may overwrite the data from the other computer who wrote a different data set, right? So synchronization is very much important to understand what is the ordering between different transactions that happen. So clock reliability is a major issue. We talked about how we can have syncs so that we can get them ordered. Think about it, right? Like if you have a stock transaction, and there are so many of those transactions happening on the same second, it's very much important for stock exchange and financial regulation to understand what was the ordering. When should something be sold, when someone bought and it's the same one. And so that happens within microseconds and milliseconds, right? So those synchronizations need to be 100% reproducible and ordered so that if there is an anomaly, that it can be detected, right? So there are multiple systems like Google and Azure, both Google and Microsoft. They have built databases that provide some sort of a logical clock. And Google Spanner and Azure Cosmos, these are highly distributed systems, databases that are available for us to use. And they provide this thing called ordering, range, and confidence. So they don't just give you the time, they give you the time confidence. Saying, hey, this time is confidence in this range. And then they also put in processes so that when writes and reads are happening, that they are actually with lower bound overlap of time. So it's a pretty big area of research even right now. These two systems, Spanner definitely provides this. I don't know about Cosmos yet, but this is a huge research area, and apart from these two systems, I've not heard of others providing this, right? Even for Cosmos, I'm not 100% sure. So unreliability of clocks is very important to understand and to set it up so that you can provide guarantees in ordering, right? Second, process pause, right? A process on this machine can depend on process from this machine. Let's say it's a it's a system that has distributed services across multiple machines. Now, it might not be able to serve all of the data for that backend call. It might depend on these two machines to give you that complete view of that backend, right? So if a machine one calls machine two, let's call it machine one, and let's say this calls machine two, and machine two just pauses, then machine one's just waiting, right? So that can happen. And then now think about multiple users, multiple processes, multiple communications, and there could be a complex graph of dependency. That could be a big problem, right? And why let's imagine, why would those pauses happen? The number one reason is the garbage collection, right? It stops the world and it collects all of those unreferenced objects, right? So that can happen. There are multiple other, you'd have to do GC tuning, you'd have to use concurrent GC collection. Hotspot provides some of that, but it's still not 100%. It doesn't completely run in parallel with application code, right? And so there are many things you have to think about. Maybe when you know that you need to do a GC, you maybe take that machine out of rotation and then get other machines to serve their traffic, and then do a complete restart or a complete GC. Let it completely clean up the world, right? That could be one mechanism. Virtual machines, right? When, especially in the cloud setup, there's multi-tenancy, right? So migrations happen, switches happen, and so that could be paused for that. Even as simple as on your own machine, you do Control Z, right? On shell, it just kills that, right? It sends a stop signal, and then the entire process is just killed, right? It could be in the middle of something, right? So there are many reasons why a process can be killed. A system administrator may decide, I'm gonna close down shut down this machine because of various reasons, and so everything that was going on can just be lost, right? So process pauses can happen. It could be that the machine is working very hard on a pretty complex job, or it could be that it's completely gone, right? So that distinction is very important. And that's why we have this thing called Quorum, which is every machine has a heartbeat, right? There's a communication happening that tells, hey, I'm alive. And there's a system that monitors, right? Each of these are monitored by this central system that says, hey, which of these systems are actually alive? And so that heartbeat actually checks whether each and every one of these machines actually alive, right? When you have that, then you can have something that you can build on top of it. When you have liveness, you can build Quorum. If there's conflict, you can say, hey, which of these machines are actually, where's majority, right? Who's actually the leader, right? So all of those things need to happen, especially when you have process pauses or process dies, and you need to take that machine out and you have to serve the client with some other machine, right? And so heartbeat, Quorum is very much important. This is even more important when you have a locking system being used across machines. Let's say there are two users, right? And then let's say you use a Zookeeper for, let's say, a lock service. Let's say user one acquires a lock, says, hey, I'm gonna I'm gonna take $100 out of my bank account, right? So let's say user one says, I'm gonna take out $100 from my bank account. And let's say user one and user two have the same shared account, right? They have the same shared account. They're two users, husband and wife, on the same shared account. He says, I'm gonna take out $100, so he acquires a lock. But then the process that was serving this user goes into GC pause, right? At the same time, the wifey says, oh, I'm going to take out $200, right? And so she acquires the lock, she gets the lock, and she writes and takes out $200. But let's say this process now came out of GC pause and says, hey, I'm going to take out another $100. That thing should be rejected because it's already, the lock is stale. It doesn't have the lock that is currently alive, right? So there's some sort of fencing that needs to happen for providing the right lock, right? So if this user acquires a lock before this user, and if they write to the system, then the database should reject those leases that are expired and when we have the latest data, right? So all of those things are super important, especially when you have process pauses like the GC pause that we talked about. And this is this just gets exaggerated when you have multiple processes, multiple systems doing the same thing at the same time. You don't want to take out, you don't want this to be overwritten by just $100 reduction, right? Because the wifey already took out $200, right? That could be a pretty big hack into the system, and now your bank is just losing money, right? So it's pretty important to understand when you have a distributed system how locking works. What are some of the issues with process pausing, reliability of clocks, because if the ordering cannot be guaranteed by the database system, because they are saying, both of these systems are saying it's the same time when we're removing the money, then it becomes a problem as to which transaction is real, which one user actually got the stock versus the other person did not get the stock, right? So ordering guarantee is very, very critical. All of this, right, assumes that there's good intention, right? But there could be also malicious users, someone trying to attack or have take down your system, maybe denial of service attack, SQL injection, a whole host of other things. So Bayesian faults are not covered here, right, in this topic. We are assuming that everyone's in the right intention, all processes are, the algorithms are accurate, right, and that the intentions are right, there's no like bad elements, right? But for that, it's a separate topic, completely out of this. But remember that as well. You have to protect your system to be secure. It has to have some sort of fencing enabled. The locking system has to be ordering guarantees, and it has to be live. It can't just go into a complete deadlock when let's say the network goes down, or let's say one data center goes down, right? So it has to be able to respond. It has to be live, and it has to be secure against all malicious intents as well, which is a separate topic. Where you can have various levels of security at the network, at the process level, and also across tenants level, which is a very big topic in itself. But hopefully this gives a pretty good overview. When you use a distributed system, it has a lot of advantage, but those advantages you need to be aware of. How do we ensure that clocks are synchronized, that process pauses? This is the biggest reason that we should understand deeply. How do we deal with them, right? And how do we make sure that our system is consistent over time, right? And so once we understand the system as an application developer, that's when the reality, right? Like we learn a lot of things in computer science when we take our degrees, but then reality is very different. Reality has a lot of these real life situations when a shark can actually eat that cable, the network can go down, there could be a fire, there could be, an accident, and a whole host of other things. That's where software engineering comes in, where we try to work and fix and not only detect failures, but we also try to recover from failures, right? It's very much important. That's why this book is pretty essential for every software engineer out there, especially who's a back-end engineer aspiring to build a career into an internet scale website, which uses multiple machines, to understand these concepts deeply so that you make the right guarantees, you use the right systems, and so your users have the best experience out there. Thanks.